Today I present lighting and rotation invariant real-time detector based on YOLOv5 vehicle wheel detector. I call it the iterative approach. So what is the problem? When creating object detectors, there are some common challenges when initially developing based on a CNN architecture. These challenges are more apparent when you try to create a model that tries to adapt to various camera orientations, lighting conditions, and environmental changes. The availability of the initial samples to cover these conditions can be an enormous challenge. The vehicle wheel is one of these examples that had been chosen to demonstrate the approach of creating a lighting and rotation invariant real-time detector based on YOLOv5. The YOLOv5 architecture is one of a simple yet powerful architecture and framework. It provides a way to declaratively provide the model definition in a YAML format instead of programmatically defining it in Python. The other powerful aspect is the image augmentation that it provides. It can be very powerful when you initially start with a very small number of samples. So the objective here is to provide a simple approach that can be used as a reference guide when developing other types of real-time object detection. The basic approach consists of following a step-by-step guideline. First is understand the immediate use case of the detector. In this case, I've built the wheel detector specifically for axle count to be used for traffic analysis and tolling systems based on visual appearance. As we can see here, these are some of the example visual views and camera orientation that we're trying to target here. Next is understanding the visual appearance of the object. We're not just trying to cover the simple camera orientation cases, but rather considering the complex scenarios that we might encounter in the final deployment. These can be things like occlusion, partially visible object, low contrast, blurriness, or other environmental changes. Next is collecting the data and following the guideline. There are three different data here. Initially, you collect real samples that emphasize the object and cover the basic scenarios. Those are manually labeled, then trained with the existing YOLOv5 weights. Then after the training is done, you analyze, look at the metrics in the performance on validation and testing set. Next is the addition of the 3D synthetic samples. And the goal is either to provide the ground truth extracted from the 3D samples, or basically use it as yet another 2D image datasets with the ability to provide variety of different shapes and visual appearance of the object that is not yet available physically. Once you get the 3D synthetic data, you automatically label it if you don't have ground truth, then manually review it. Then you train with the previous weights from the previous training session. Then you repeat, you analyze, look at the metrics, and run detections on the validation and testing set. The next is introduction of real samples gathered from public image datasets. Then those gets automatically labeled with the most recent model update. and manually reviewed, then training with weights from the previous session, then you analyze the final metrics, again, do detections, and the final phase would be the final deployment, where you gather the images from the final use case and you do automatic labeling, manual review, train with previous weights, analyze, and repeat. That would be an infinite cycle for the model. The training data, the initial ones compose of 72 manually captured images to cover the various camera angles and the basic scenarios that we're trying to cover here. These are the 3D synthetic images that I used. I gathered the 165 images. I did not have a ground truth data labels, but I used the previous weights of the model to automatically label these and fine-tune the bounding boxes. Next is the real samples from public datasets. I decided to use comp cars because it provides a comprehensive collection of car make and models. I manually selected 827 samples to cover a variety of wheel shapes, angles, and environmental changes. Next is the open images. Those have been selected to provide final view that imitate the final use case of the detector. I manually selected 179 images to cover a variety of the cases and provide also complex scenarios to handle. How did the model behave? If we look at the metrics here, initially the model, it did not perform as good as the introduction of the synthetic data. But the interesting part was the introduction of comp cars has improved the metrics of the mean average precision, but the following data set, which is the open images, performed worse in this case. And here I'm showing the cropped images of the open images, and that has performed better and close to the previous performance. And we can look at the next metrics. So if we look at the loss, again, same behavior. We can clearly see that the open images, the blue, is actually worse. It's not manifesting here in the object loss, but we can clearly see it in the box loss. The box loss shows a significant change compared to the previous comp cards. Why did this happen? That apparently all comes back to the input size of the detector. Most of the open images are rectangular sizes, and the vehicles presented in them are actually small, and the wheels are even smaller. Then I did a test where I did a cropped square view out of a rectangular view. And if we look at the van highlighted with the red arrow here, the bounding boxes around the wheels are loosely tighted compared to the square size input. And that suggested that the best way to handle incorrect aspect ratio is to basically try to crop to the region of interest and train on those cropped views, and that was the solution in my case. So here we can visualize how the input size optimization can have an effect here. I trained on a square size for the reason that square can minimize the amount of padding that needs to be added to a rectangular image, but yet the problem is going to still arise when you use a rectangular image, but the content within the rectangular image is small. And in this case, it will be problematic. Let's look at the final detection of the latest model update. It actually performs very well on, again, these are square or close to square aspect ratio. Here are example showing on the right side the wheels being detected even though they were being occluded with other objects. This is another example where it shows detection from a very steep angle and also a very low resolution sizes. The farther vehicle on the right side, they have been able to detect the wheels on those. This is also a very similar example. We can clearly see like the very small vehicles. The model was able to detect the wheels on those, which is a significant improvement. In conclusion, the vehicle wheel detector model has reached the reliable phase, and it's a very good starting point for further improvement when deployed for the final use case. I would say the iterative approach give insights needed to correct mistakes early on in the process. And it's so important to understand why the model behavior changes and how you look at the metrics to give clues, and also visual validation by testing. Those are very important key points to create a reliable model. I hope this was very informative and to encourage building a detector with that approach. Thank you.